Namaste and a warm welcome to week 7 of the course on mathematical foundations for machine learning. In the first 4 weeks we looked at the idea of linear algebra. We went on till singular value decomposition and applications and so on, and then we started off with the ideas of probability. We looked at the basic probability foundation still Bayes theorem in week 5. In week 6 we looked at the idea of random variables, and then we looked at characterizing the random variables or describing the random variables in terms of the probability mass function or the probability density function or the cumulative distribution function or the moments. And towards the end of week 6 we had a question. It is not always that the random variables appear alone. You may have multiple random variables to be occurring together. One of the examples that we took last time was like look at the cost of petroleum products. The moment the cost of the petroleum products increases, it is going to have an impact on the essential commodities price. This is something which we always see. Similarly, when you transmit a signal, you can have atmospheric disturbances to add noise to the signal. Therefore, the received signal that you are going to have is going to be a combination of both the signal as well as noise. Now, the question that we have is, in places where we have multiple random variables to be occurring together, how do we characterize or how do we study them together? An analogy that I gave in the last class was saying, so assume that there are two kids. There is this one kid which has a behavior which is well known, it has its own behavior in the house, and let us say there is another kid which has its own behavior in its house, and assume that these two kids are friends and then they meet at another place. Now their joint behavior is going to be something else, which most of us would have seen. When the joint behavior is different, how are we going to study them? So there are questions that arise in case of this joint behavior. What is that? Number one, is the behavior of one kid going to impact the behavior of the other? If yes, in what way? Is one random variable change in one random variable, or if one random variable if there is an increase in one random variable, is it going to result in increase in the other random variable, or is it going to decrease, is it going to cause a decrease in the other random variable? Or the third question is even more important, are they independent of each other? Is the change in one random variable not going to affect, or is one random variable independent of the other? These are the questions that we have, and especially in machine learning, when you talk about, we get into the idea of multiple features. So we look at individual features, you look at independent features, so you have a whole lot of stuff that you look at. So what we are going to do is, in this week we are going to study about jointly distributed random variables, and the moment two random variables come into picture, it is like the same thing that we studied in probability. As long as we had a single event or disjoint events, we did not even bother much, we did not really pay we just know that okay, probability of A union B was P of A plus P of B if A and B were disjoint events. The moment A and B events, the events A and B had an intersection, we got into trouble. That is where we asked, like, can occurrence of one event give complete information about the occurrence of the other? Can occurrence of one event give no information upon the occurrence upon its occurrence about the other event? Or can I get some partial information about event B upon the occurrence of event A, in which case we were actually looking at some finite intersection that was there. Therefore, we said that okay, mutually exclusive events were ones where occurrence of one event gave the complete information about the occurrence of the other. And we also said that occurrence of one event does not give any information about the occurrence of the other when the events are independent. That means the posterior probability of event A given B was equal to the prior probability of A. And the third thing that we said is okay, when you want to look at partial information or partial update about the other event, we were looking at the idea of conditional probability, which is P of A given B or P of B given A. It is exactly the same thing we are going to look at here. Whatever we studied in terms of pairs of events, we are now going to put it across to pairs of random variables. Suppose I have two random variables. The question that I ask now is, I have two random variables. Are they independent? Are they not independent? If they are not independent, what is the information? We always have this, like given that this feature is there, like what is the chance or what is the probability that it belongs to this class? That is a question that we often have in machine learning, right. So those things, like whatever we studied in terms of events, are now going to be, we already saw that event space getting mapped to the random variable or the range of the random variable, and we said that okay, we could map using the random variable was basically taking you from the event space to the set of real numbers. We had that. Now what we are going to do is we are going to look at pairs of random variables. Once you know pairs of random variables, you can always extend it to any n dimensional random variable or look at n random variables together and so on. So the first thing that we are going to do now is we are going to look at jointly distributed random variables. Jointly distributed random variables. We are going to look at jointly distributed random variables. Now what do we mean by that? Suppose I have two random variables, let us say x and y. Let x and y be two random variables you can take x and y to be both continuous or x and y to be both discrete. How are we going to capture their joint behavior, right. So what we are going to ask is, how do we study the joint behavior of x and y? In the case of events, your P of A intersection B was giving you the probability of both events occurring. Can I do something like this here, right? Recall in case of two events A and B, defined on a sample space omega, P of A intersection B gave the probability of the occurrence of both. Gave the probability of occurrence of both A and B. Now what I want to do is, can I do the same thing here? If that is the case, how do I study this joint behavior? So we are going to do this. So let x and y, we have already taken to be two random variables. So we are going to say, specifically we will put it this way, let x and y be two discrete random variables. right. Let a and b let x and y be two discrete random variables. Now what I want to do is we are going to look at the same thing, p of a intersection b. Remember, you can define probability only for events, therefore I want to use that idea here. So what I will do is I want to look at the random variable x and y together, I want to study them together. So what I want is I want to look at probability of x taking the value x and y taking the value y, right. I am going to look at this exactly along the lines of this guy p of a intersection b, exactly what I have here, p of x is equal to x and y is equal to y. So what do I have? I have the probability of, let us say, x taking the value x intersection y taking the value y, and that is what I am going to call it as the joint probability mass function. Let us say I will take x is equal to xi and y is equal to yj. So it is easy for us to write it here. So I am going to say p x y of, let us say, xi comma yj. What does it say? It says the probability of the random variable x taking the value xi and the random variable y taking the value yj, that is basically what we call as the joint probability mass function. So this we are going to call as the joint probability mass function, joint probability mass function. Right. Now what does it mean? Say for example I have x is equal to, let us say, head comma tail. X is going to be a random variable, it takes the value head comma tail, which means it's an outcome of Bernoulli experiment. So head and tail, let's say map it to 1 comma 0 or 0 comma 1. So x takes the value 0 comma 1, and let us say y is basically the random variable associated with rolling of a 6 face die. So the value that is you are going to take is 1 2 3, that y is going to take is 1 2 3 4 5 and 6. Now what is the question that we ask? We ask for probability of, let us say, x is equal to 0, y is equal to 2, which is nothing but p x comma y of 0 comma 2, right. This is basically the joint probability mass associated with 0 comma 2. So how do we put all these things together? Let us say that, okay, I have my table, I am going to capture my joint probability mass function in terms of the table here. I am going to put it in terms of a table. So I am going to have this. So I have, let me take y to be 1 2 3 4 5 and 6, and x is going to be 0 and 1. So I am going to have a probability which is p 0 comma 1, p 0 comma 2, p 0 comma 3, p 0 comma 4, or p of 0 comma 1. So you can write this as p x comma y of 0 comma 1, p x comma y of 0 comma 2 and so on. So you can fill this table. So I am going to have p 1 comma 6. So these are all the individual probability values or individual probability masses associated with that. So what we are going to see is, in this case the probability mass function is going to be expressed in a 3D space, right. I have x axis and the y axis, and the probability mass is going to be along the z axis. So we have a 2-dimensional random variable here, which is like basically x comma y. Now the first and foremost property that we need to identify here is the following. It says that, look, the joint probability mass function p x y comma x comma y, okay, let us say our this value p x comma y of let us say xi comma yj. Since this is a probability value, its measure cannot be, its value cannot be greater than 1 and less than 0. So, it is always a value between 0 and 1, right. And remember, when we did the single random variable probability mass function case, we said that you add all the probability masses, you get the unit probability mass. Basically, it was the unit probability mass which got distributed among all the values that the random variable could take. Now, in this case what we are going to do is we are going to look at this, we are going to say look sigma p x comma y of x I comma y j summation over all I and j is going to be equal to 1. Now, what does that mean? You take all these values which are here, you take all the values which are there in the table, add all of them and that must get you a 1, the sum must be 1, right. That is interesting. The third point is even, the third property that you have is even more interesting. What are we going to say? We are going to say that look, suppose if I add all the probability masses along the row, the first row corresponding to 0, I am going to add all the probability masses. It is like saying look, I have 2 rows of let us say 6 people standing together. If I add all the weights of these 6 fellows in the row corresponding to 0, what do I get? I basically get the total weight of the 0th row. Similarly, if I add all the weights of say those 6 people who are standing in the row 1, you add all of them, I basically get the total weight of the row row 1. So, if I add this, so I am going to say fix the value of let us say y and then what you do is you add the values of probability masses along the x direction, you get what is known as the marginal probability mass function. That means we just got the total weight along a particular row, that is basically called as the marginal probability mass function here, because you are going to add probability masses here. So, the total probability mass that you get along a row will correspond to the marginal probability mass function. So, I am going to do this summation over all j p x comma y of x I comma y j. That means you fix x I, that means you fix the value. For example, here I will fix x is equal to 0, I add all these values. So, what do I get? I basically get p x of x I. Similarly, I will fix the value of y p x y of x I comma y j. I fix the value of y which is basically a yj and I sum the probability masses over all I. That means I am going to fix the value of y which is say 1 and I am going to add these 2 probability masses. We said we had 2 rows of 6 people. Now, what I am going to do is I am going to add the weight of those 2 people in every column, right. In every column I am going to add, there are 2 people going to be there in this, if you look at this table. Now, what I am going to do is I am going to add the weights of these 2 guys. So, what do I get? I get the total weight in the first column, then I get the total weight in the second column, total weight in the third column and so on. So, this is going to give me my p y of y j, right. So, these 2 are called as, these are basically the, we call them as the marginal probability mass functions. Let me write it. These are basically the marginal probability mass functions, right. We can do this. This is, we are just dealing with the case of a discrete random variable. So, we get this, right. Okay. And you remember when we said p x comma y of x I comma y j, this was basically probability of x equal to x I intersection y equal to y j, right. This was basically my p x comma y of x I comma y j, this was the joint probability mass that we had. Now if you look at here, something interesting happens. This is basically like saying I have this event A and I have this event B. So I am looking at P of A intersection B, and whenever we talk of P of A intersection B, there is a possibility that P of A intersection B could be equal to P of A into P of B, in which case you call A and B to be independent events. So now what we are going to do is we are going to say if P of x equal to x I intersection y equal to y j is equal to, there we said P of A into P of B, the same way I will do here, I will say P x of x I into P y of y j, right, P y of y j, then we will add one more clause, okay. Then it is not even then, for all values of x I comma y j, for all values of x I comma y j, then we say that the random variables x and y the random variables x and y are independent I mean this definition is not something new, we already know that if you have two events A and B and probability of A intersection B is equal to probability of A into probability of B, then you call the events to be independent. In this case what we say is the random variables x and y are independent if the joint probability mass function of the random variables x comma y is equal to the product of the marginal probability mass functions of x and y at every point x comma y or x I comma y j, then you say that the two random variables are independent. Suppose if it does not, at one point it fails, then you still say that look the variables are not independent, is that clear? It has to be true for all pairs x comma y or x I comma y j. If the product of the marginal mass function is equal to probability mass function is equal to the joint probability mass function at all points x I comma y j, then you say that x and y are independent random variables. I will come to the idea of conditioning a bit later, but we will just look at this notion of independence and stuff, right. Similarly we can do all these things for our continuous random variable too. So suppose I take x and y to be both continuous random variables, then let us look at what happens. So let us take this, suppose x and y are continuous random variables, then we had this, what was that? We said look I have, in case of discrete we said probability of x equal to x I intersection y equal to y j was the joint probability mass function. In case of continuous random variable, however, we cannot look at probability of x equal to x I and y is equal to y j. Why? Because the point probability mass is 0 in case of continuous random variable. So we cannot define the probability mass function or the joint probability mass function like what we defined the probability as the probability density function, here also we have probability density function, then we define we have this what do you call our joint probability density function. We define f x comma y of x comma y is equal to probability of, this is again there, x less than or equal to x plus delta x, x minus delta x, right. We are going to do this, we are going to put this as p of x minus delta x less than or equal to x less than or equal to x plus delta x, and y minus delta y less than or equal to y less than or equal to y plus delta y is equal to integral minus infinity integral x minus delta x to x plus delta x, integral y minus delta y to y plus delta y, f x comma y of x comma y dy dx, where f x comma y of x comma y is the joint probability density function. Is the joint probability density function. So, now what are the properties of this? The first and foremost property is, we saw that in case of discrete, the what we say, we said that look, the summation of all the probability joint probability mass functions or joint probability mass values that you have was equal to 1. Similarly, in this case we are going to say integral minus infinity to infinity minus infinity to infinity f x comma y of x comma y dy dx is equal to 1. That means, here if you again if you recollect, just some time back I said that look, you are going to have this probability mass function to be along the z axis, that means you have along variation along x and then y, these are the two random variables. So, the probability mass function is basically pointing towards the z axis. In the same case we are going to have f x comma y of x comma y, which is basically the joint probability density function. This is going to be along the z direction. So, it is going to be, you are going to look at a 3D surface here. So, it is going to look something like this. Right. So, it is going to be looking like this. So, I have my so, I am going to take this, let us say, let me do this. So, it is going to look like this. So, this basically is the volume that you have. So, I have this is along the z axis and let us say this is along the y axis and this is along the x axis. So, suppose if I put it this way, then I am going to have the elemental volume dy into dx is going to give me an area and this is going to give me the height. So, what I am going to say is the volume under the joint density function is going to be equal to 1. So, this is something which I have. Like how we said, when I have joint probability mass function, I added along a particular row, I got the marginal probability mass function of let us say x equal to xi. I added along the column, I ended up getting the marginal probability mass function of y equal to yj. Can I do something like that here? Yes, of course you can do. So, we can do this. What is this? We say that integral minus infinity to infinity f x comma y, that is you just integrate the joint probability density function with respect to y, what we get is the marginal probability density function of x, and similarly you take the joint probability density function and integrate with respect to x, you end up getting the marginal probability density function. So, you are going to call them as marginal probability density functions. Again the question of independence comes, right. We have probability of A intersection B, we have probability of A, we have probability of B. Suppose if P of A intersection B is equal to P of A into P of B, then you say that the random variables are independent. The same is the case here, the fourth one, if f x comma y of x comma y is equal to f x of x into f y of y, then x and y are independent. In fact, the other way also holds good, if x and y are independent. So, I will just put this x and y independent implies the joint probability density function is equal to the product of marginals, right. This is what we have. Of course, you will take this to be a cube. So, I mean I have not been able to draw it in to the scale here. So, let us forget about that. So, this is basically the idea of independence of random variables. So, what does it say? F x y of x comma y or p x y of x comma x I comma y j is basically the joint behavior. F x of x, f y of y, p x of x I, p y of y j, they are all the individual behavior. Now, what are we trying to do? We say that if the joint behavior is going to be like what we had here, the product of individual behavior or the product of their marginals, then you call them to be independent. Otherwise, you want to study whether they are going to be, there is going to be any kind of relation between these two. And we have one more question here, like in case of the single random variable, we also defined the cumulative distribution function. Therefore, I have a question. So, can we have cumulative distribution function of jointly distributed random variables? Of course, you do have. We can talk about joint CDF of two random variables x comma y, right. We can talk about joint CDF of two random variable x comma y. So, which is basically given by the same notation, capital letter F sub x of sub x comma y of, let us say, x comma y is nothing but the probability of x taking the value less than or equal to x and y taking the value less than or equal to y, right. In fact, this is also a complete probability model for the random variables x and y. So, this is a complete probability model as far as x and y are concerned. Now, what does that mean? It is going to be something like this. I have let us look at this. So, I have my x here and I have this y here. Let me take x is equal to x here and let me take y is equal to y here. So, what am I going to look at? I am going to look at the probability of x less than or equal to x, which means I am going to have a boundary here x less than or equal to x, and I am going to have a boundary here which is basically my y less than or equal to y. This is what I have. So, so this is basically the point x comma y. So, what I am looking for is basically here. So, this is going to be my entire region of x less than or equal to x and y less than or equal to y. So, I am going to look at the probability of this. So, this is basically the joint CDF. And again you can look at the properties of this joint CDF. These are all pretty straightforward extension of your single random variable. So, let us look at the properties of joint CDF f x comma y of x comma y. So, the first property, like what we did in the case of single random variable, this f x of x comma y, f x y of x comma y is basically a probability value, which is p of x less than or equal to x and y less than or equal to y. Therefore, I am going to have this first property, which is 0 less than or equal to f x comma y of x comma y less than or equal to 1. This is the first property. Remember, we wanted to get the marginal probability mass function or marginal probability density function from the joint probability mass function or the joint probability density function. The same is the thing that you can do here. So, I have the marginal cumulative distribution function of x. This is basically called, this is the marginal CDF of x. So, I have f x of x is nothing but the joint cumulative distribution function of x and then less than or equal to infinity. That means y value, you sum up all the values. So, you are going to get this, right. Similarly, I can do this, the marginal cumulative distribution function of y is nothing but f x comma y of infinity comma y. This is interesting. And we had another property which was there in case of our CDF of a single random variable, which said that f x of infinity is 1. So, I will write this as f x of f x comma y of infinity comma of infinity, which is 1. Then I am going to have the fourth one, which is nothing but f x y of x comma minus infinity is equal to 0. Similarly, f x y of minus infinity comma y, that is also equal to 0. And the most important thing is the following: if x is say less than or equal to x 1 and y is less than or equal to y 1, then f x comma y of x comma y is less than or equal to f x comma y of x 1 comma y 1. These are some of the important properties of cumulative distribution function. The last one is even more interesting. I will do that now. Recall, we had this, recall probability of, let us say, a less than or equal to x less than or equal to b was basically f x of, okay, it was probability of probability of a less than x less than or equal to b was basically f x of b minus f x of a. This is what we had, right. We said that this is basically we obtained this property by taking disjoint union of the set, which is nothing but probability of what do you call x less than or equal to a union a less than x less than b, that was equal to probability of x less than or equal to b. So, that is how we had this property. Now, what I am going to do is I am going to put a constraint on both x and y. So, I am going to have probability of x 1 less than or equal to x 1 less than x less than or equal to x 2 and y 1 less than y y1 less than y less than or equal to y2, we have to get something, we have to get, it is basically, what is this probability? I want to find out this. So, it is going to be something like this. What is that? This is along x and this is along y. So, let us take this is y2, let us take this is y1 and let us take this to be x1 and take that to be, let us say this is x1 and that is x2. So, what we want is we want basically the probability of this. We want this probability. It says x1 less than or equal to x2, y1 less than or equal to y2, therefore, you basically get a rectangle here. We want to find out this probability is nothing but this is equal to, sorry, this is equal to f x comma y of x2 comma y2 minus f x comma y of x2 comma y1 minus f x comma y of x1 comma y2 plus f x comma y of x1 comma y1. If you see the same index, they are added and the cross index term are basically subtracted. So, this is basically I have x1 comma y1 this point, this is x2 comma y1 and this part is x2 y2 and that point is x1 y2. So, this is what we have. Okay. Now, where do we go from here? We looked at the representation of joint behavior of two random variables in terms of the joint probability mass functions, joint probability density functions and joint cumulative distribution functions. The most important thing that we want to look at now is what are these joint moments? Do we have something called as joint moments in the first place? We had moments of a random variable where we looked at mean, variance and so on. Can I have something similar to that here? If that is the case, what are those moments called? Do we have some specific names? What are their significances? And we have still not gotten into the idea of conditioning. So, what we will do is in the next class when we come back, we will look at the idea of the joint moments. We will try to get some really good insights about these joint moments, why are they important, and in fact we can talk about what you call the relation between the random variables in terms of these joint moments also. So, we will come back when we come back in the next class, we will look at the idea of joint moments and follow it up with conditioning of random variables. When you come to conditioning of random variables, there are two things that can happen. One is you are going to condition a random variable with respect to another random variable, or the other is you could condition a random variable with respect to another event, right. So, we are going to look at that. Maybe we will also look at a bit of we will also look at Bayes theorem in terms of this random variables and so on. So, that will be the focus of the rest of the topics in this week. When we come back next, we will look at the joint moments of the random variables. Namaste.